data loss. It's sort of a weird thing. This has been around from the very start, because if you lose data, it's not good in a messaging system. And 10 years ago now, we actually started Aeron. It's kind of interesting. So we haven't really talked that much about it, so we've got a birthday this year. And this is the sort of stuff that it's kind of like the janitors of the building. It gets ignored. People don't really think about it, but it's really important. And kind of why do we do this and why do we care? Because we've not needed to talk about it much over the whole time. So let's touch on some of the concepts behind it. So probably all heard of TCP, heard of UDP. Well, kind of what's some of the differences here? Well, TCP historically has been used very much for synchronous communication. So a bit like having a telephone call. You know someone's on the other end, you're having to and fro of communication all the time. And actually, information theory going right back to the 1940s and things like Shannon's fundamental paper on this, he points out that doing any really good communication requires feedback. It's fundamental if you don't have feedback. And if anybody has any doubts about the importance of that, go home, have a conversation with your partner, and if you don't get feedback that they actually understand what you're saying, you can guarantee you haven't communicated well. So the feedback is crucial to this. Now, UDP is kind of interesting. It's very much fire and forget. It's one way. Some people think about it, like Nate described it as a postcard. It's a very fast postcard that you can send, but how do you know that it's got there? Like, do you phone up the person you sent it to later? Do you wait for them to tell you that, oh, I see you had a nice holiday and you sent this postcard to me or something? But yeah, it's the postcard. But kind of interestingly, with UDP, that can be a postcard to many recipients. So it's a great way to disseminate information. And that's a lot of behind why we went the way we did with Aeron. So when things go wrong, we end up having to handle data loss, and it's very much like the different stages of dealing with grief and various things. And you'll probably all be aware of these sort of 5 steps to dealing with it. Usually around steps 2 to 4 is where people call support and want help. Usually you'll get a phone call on this. But kind of interestingly, some people even go for the next stage. So go to the last stage and just kind of accept that data loss happens, which is kind of interesting. So I remember it's getting on for about 5, 6, 7 years or so now. I had a customer call up and says, "Do you know what? We want data loss just not to be handled." Okay, that's kind of interesting. Why would people want to do that? And they had a really interesting case. Anybody heard of ad trading? Like when you're on the web and you get an ad posted in your browser as you're looking at something else, there's exchanges where your eyeballs are basically traded for that. Somebody can compete with a price to have that sort of moment in front of you based upon certain demographics about you. And it goes at phenomenal rates. Like we're talking exchanges that are often higher volumes than you get in financial exchanges. But imagine if you get so much data that you just lose some. What about you just don't care? You don't try to recover. You don't deal with it. You just get the next ad. So it's kind of interesting. Some people just don't care. But we want to care in this case. But by the way, you can turn off the data loss handling in Aeron. By default, it's not turned off. It's on all the time. But you can turn it off if you want to. So it's kind of interesting and different. So how do we deal with it? So what are the stages beyond this? Well, if you don't get data, you got to say you haven't got it. And by doing that, we send a negative acknowledgement. So the negative acknowledgement goes back to the source and say, I never got it, didn't get here in the end. So please send it again is effectively what you're asking. And so, like, what's a simple solution to this? Well, you've got to know the data's gone missing. And one of the easiest ways to know that data's gone missing is you just put a sequence number on every message that you send. And if you receive messages 1, 2, and then you go to 3, but 3 doesn't make it for some reason, it gets lost somewhere in your network, and then you get message 4. At the other end, you now realize on the receiver, I've got 1, 2, and 4. Where's 3? 3 has gone AWOL somewhere. And by the way, if this happens, It's not very likely because some gamma ray hit one of your cables and flipped a bit and lost data, which is the sort of stuff you're taught at university and how it happens. It's usually misconfiguration. Some buffer's the wrong size, data didn't fit in it, it spilled on the floor. So getting your configuration right is one of the major things to not having data loss. But if the data is lost, we've detected that that gap occurs, we need to send the negative acknowledgement back to the sender to have that data retransmitted. And that's kind of the basic way that most of this sort of happens, and it's a kind of simple solution. But do we just simply send this NAC? Could anything go wrong? Anything possibly go wrong? If you spend any time in networking, you realize an awful lot can go wrong. So this, I'm just going to send a simple NAC, is often not that simple. There's many other things that need to be considered. So let's look at how would the simple solution in the simplest way need to work. Well, on the sender, you need to keep a buffer. You need a history of the messages you're going to send. And you send the data, and if anything's lost, you get the NAC, you've got that data to retransmit it again. You're able to resend that data again. And at the receiver side, the only real responsibility is you notice that you've got missing data and you send the NAC. So that's the simplest possible solution. Like, is that a really good or bad idea? You sort of think, well, what can go wrong? Like, anybody heard of things called NAC storms? And all sorts of nasty things that can kind of happen in this world. And if you've actually dealt with any messaging products where people thought, yeah, UDP is really cool, let's do lots of stuff with it. I remember 20 so years ago, lots of the messaging solutions out there were pretty terrible when things started to go wrong, because various things happen and it's not nice. And so the simple solution often needs to get a lot more complex. There's a lot of things you've got to start adding to this to make it work well. And effectively, some people think, well, I'm going to end up just implementing TCP anyway on top of UDP as a way of doing that. So kind of like, what's the point? Like, so why does someone start off down this route? Well, I can tell you the main reason why it's the point in the likes of Aeron, multicast. Multicast is the real reason to why most of this happens, because we want to send data to multiple recipients. So when Aeron was created over 10 years ago, customers we were talking to are fundamentally doing multicast. Most of this was IP multicast at the time. You're disseminating market data, execution reports. It's usually fanning out data to multiple recipients, but also sending data into multiple recipients and achieving fault tolerance and various other things. And so it becomes kind of core to doing a lot of this. And the replication happens in the network. So you send a message to a multicast group. The network then does the replication for you, and it gets to multiple receivers. And the receivers receive this. Now, what's interesting is when the loss occurs, it can happen in all sorts of interesting ways. So it can go missing at the source, could go missing at the end of one of the receivers, could go missing somewhere in the network in between. Now, quite often, it's correlated. Loss always ends up correlated. So somewhere along the tree, this loss starts to happen, and we've got to make decisions on how do we deal with it. What do we do going forward from this? So what do we do? Well, what should we do if the receiver notices a gap? Like, does it go back to that, well, I just NAC? Maybe there's certain issues around that. Like, so I'll send the NAC straight away. Do I send the NAC eventually? Or maybe I just don't even bother and care in this sort of case. But so thinking about when do we send the NAC is kind of interesting. So just kind of exploring that space. But what does the sender do? Like, whenever it gets a NAC, does it just respond straight away? Does it respond to everyone? Does it do it eventually? Or does it just ignore? So these are just like kind of fundamental questions, but it all comes down to time. Time is the really interesting thing in most distributed systems. And most people don't realize this because once you're distributed, you're physically separated, you have latency, things take time. Right, Lamport talked about this right back in the 1980s. It's kind of fundamental. And the fallacies of distributed computing talk a lot about how everyone expects latency to be zero. Well, it's not. And even when you're working in the low latency space and you get to play with some of the best network kit, where it is very low latency, it's still not zero. It's never zero as a way. So you need to be aware that latency is a thing. Physics is a thing. And then people talking about computer science about, well, it's not physical, it's a virtual world. Well, sorry, it's rooted in the physical world, so some of the things still apply. And it influences what we do. So when we deal with the multicast world, like, what should we effectively do in this world? Like, so if receivers receive this, when do they NAC? Well, they shouldn't NAC straight away, because that's how you get NAC storms. Because if you NAC straight away and everybody sends again, you're basically just pouring fuel onto the fire, and the world gets really bad. What's interesting is, when do you NAC and how do you NAC? So I'm just sort of saying here, random back-off timer, but there's a lot of fundamental theory behind that. There's some really good work that was done in the 1990s based upon some things that happened in the 1980s by a woman called Sally Floyd. And she did some of the seminal work on how we deal with multicast and how we deal with loss. Turned out she's a brilliant computer scientist, but that's not how she started. Her undergraduate degree was in sociology. And she basically realized that large groups of people behave in certain ways. And actually, systems of computers are very similar as well. You can't deal with them very precisely. You deal with them in kind of really interesting ways. And so one of the things that she put forward was, if you see loss, what you do is you don't react straight away. You set a random timer for some point between now and a time in the future. And that time in the future is usually based upon what is the round trip time between the sources and the receivers of data. And you use a small number of multiples of that time to set your range for your random timers. Now that random timer goes off, you then send the NAC. And if your timer goes off and you've already got the data, you don't need to send the NAC, because somebody else is going to have a random timer that's going to go off at the same time, within the same time period, but over a distribution. Now that work has been taken much further forward, because she proved how well this worked just with a standard distribution. And then a bunch of nice French mathematicians looked at it and went, actually, that's not ideal. How about if we take that distribution, we skew it all towards the back end, but we chop off enough for the front so we get a probability of something happening sooner, but most of the NACs end up in the back end for a given size of population. Turns out to work even better. It's really nice. So just how randomness works really well inside this. And so you get a high probability of one receiver realizing that the data's missing and sends us NAC quite quickly. But you've got lots of backup by, if that doesn't happen, things happen later, but it's all skewed towards the back with increasing probability towards the back end. So you're sure it's going to happen. Then on the sender side, these NACs are coming in, but there's also a possibility you're going to get multiple in at the same time. Even though you have skewed the results, it's still possible that'll happen. So if you see the same NAC that you've just dealt with and sent the data, well, you just ignore the NAC again. And you do this all for periods of time, because time is a thing in this space. So you avoid this. Now, there's some very simple rules. You start to apply them, and all of a sudden, things like NAC storms and all that horrible stuff that came about from people who played with networking technology and didn't understand some of the basics just don't happen. And especially in the multicast world, like, Aeron's been out there and live for 10 years in this sort of space. And when it comes down to support issues and multicast and loss handling, zero. We've not had anyone ever complain about it, which is kind of nice. So it kind of just shows that some of the fundamental theory there just works, and it works really well. So what does this look like? So scenario A, we send some data. We realize that it gets lost and the gap is detected by multiple receivers. So what they do is they each set their randomized timer. Receiver A's timer goes off first. It sees that the data hasn't been retransmitted, so it sends a NAC. NAC goes back to the sender. Sender retransmits the data, goes to the network, gets retransmitted to the multicast group, so that means everybody gets it. Receiver B, its timer goes off a bit later. Its timer's gone off. Data's here. I'm just canceling it. Fine. Don't need to do anything else. No drama. Everything just works. Kind of goes forward. This works really nice. The flip side of it is the two timers fire within a close enough window for the round trip. So You don't see that the data is there for receiver B because receiver A has sent the NAC, but you send the NAC from both of them. It gets suppressed on the sender because you just ignore it because you know you've just sent that data and it's going to get there anyway. And so it just smooths things out nicely. So why this UDP and TCP, and why even the different approaches that we take? Well, if you actually look at the history of TCP, it's very pessimistic. It was deliberately pessimistic from its early design. It was running on networks that were very inferior to what we have today, very low capacity, actually relatively high latency, high levels of loss, and highly contended. So it starts off from the whole premise of, I'm going to be super careful because I'm using this precious resource that's actually quite brittle. And so it does things like slow start. So it starts a connection and ramps up the amount of throughput it'll send until it starts to see problems and then starts to back off. So it's being ultra cautious in how it works. So that's a nice safe way to work when you're in that set of environments. And it's also acking the data all the time rather than NACing. So it's positively, so basically it's starting from this very pessimistic, it's like, I'm taking a step, is everything okay? Yeah, fine. Take another step, yeah, it's okay. I can start to walk a little bit faster. And that's just the approach. And it also does some crazy stuff. Well, it seems crazy to us, but completely reasonable when you think of TCP. Like, if it hasn't sent data for a while, and it's going to start sending data again, it goes right back to starting being really careful because it thinks the world may have changed. Now, how long is that period of time? Often between about 200 and 500 milliseconds. So like well less than a second, it's going back to being slow again. And that's how it works. It's focusing on that world. Now, Aeron, completely different approach. We want to be optimistic. We believe we're running on networks that are well provisioned and work really well. So we don't start slow. We actually start at what we think is a reasonably fast speed to go. And if that is too fast, we back off. So it's not that we're going to destroy things. We just start from a different premise because that's typically how a finance network is. And it's well provisioned with lots of capacity for this world to do. And because we're also optimistic, we just assume data is going to get through unless we're told it isn't. So the thing about TCP is like, are you sure? Are you sure? Are you sure? It's taking that sort of approach. With us, it's, yeah, we're going for it. Tell us to stop. If it's the way. So it's a different type of approach, and it fits quite well into this world, particularly when finance is one of your major customers or games or some other thing. So it works kind of well. So like when you say Aeron is super fast, run it in a typical data center against TCP, it's not a fair comparison. It's much faster. Now, take Aeron and typical TCP, and you go run it in a hotel lobby or at a conference or something where there's loads of people and you're doing it all over Wi-Fi and it's all contended, TCP is going to win hands down because that environment's not well provisioned and able to cope. So it's horses for courses. It's not good. There's not good and bad with things. These are engineering trade-offs and different approaches to have. But what's really interesting is like we all use the web. Do you know that actually for most things you do on the web these days, you don't use TCP anymore? Because it's not a good fit for most modern things. You're using protocols called QUIC and HTTP3, and they're UDP based. And what they get out of it is they get much faster connections, they get much lower latency and better throughput in many cases. So a lot of what we're doing in Aeron is now starting to be copied in some of the other things, although fundamentally they're doing it to be point-to-point, not multicast as a world. So the point-to-point is an interesting world to consider. So if we're point-to-point and unicast, is the world the same? Well, we could probably simplify things quite a bit in this world. We don't need the randomized back-off timers because we don't have multiple receivers. We can, in theory, NAC straight away. NAC as soon as a gap is detected. And that's pretty much the approach we've taken for nearly 10 years. And no one really complained about it until recently. And I'll tell you a little bit about why, which is kind of interesting and why we've changed some stuff. So how do we basically work? And unicast and multicast are kind of similar. So Aeron doesn't apply sequence numbers to messages. It transmits packets of data, and the packets have an offset for where they are in the stream and a length of that packet in bytes that it's going to receive. And it's all part of the protocol and data structures that we have, where basically it's designed as a complete system with a holistic approach. So that allows us to do quite efficiently. So the offsets that we put in the packets, also the offsets go into the data structures at the other end. So it makes it all nice and efficient on that. So I'm maybe sending data starting at offset 0 in the stream. It's got 50 bytes, goes there. Then I start the next one at offset 50. It's got 100 bytes from there, and so on and so on. And then all of a sudden I'm sending these packets and I get data loss. So a packet gets dropped. Another packet comes along later, different offset, where that offset is now further ahead than the previous offset plus length. I've got a gap. That's a problem. In fact, I have multiple packets missing as a gap, and I'm able to see that. Now, Aeron doesn't NAC and ask for each individual packet. It says, I've seen a gap. In fact, I don't know how many packets were in there, but there's a range. So it just sends a message back as a NAC saying, at this offset, I've seen a gap, and it's this length. So now you're able to resend the data. And this is quite cool in other ways, because the people who've read the blog and stuff, they talk about things like smart batching or natural batching. If we realize 2 or 3 messages have gone missing, and they would have been 2 or 3 separate datagrams, if they fit in one, we just put them in one, send it back again. And so it works quite efficiently, even in the recovery scenarios. It's a kind of nice way of working. It gets interesting if there's a larger gap. So what if the data that has gone missing is way more than a datagram? So now a typical UDP datagram on a network will be 1,500 bytes that fits into an Ethernet frame. And this kind of thing is it's like turtles all the way down. Things are wrapped inside things, wrapped inside things. Pretty much Ethernet is everywhere now in the world. I'm old enough to remember things like slip networks and frame relay and all sorts of other stuff that was out there in the past. Ethernet is everywhere now. That's pretty much what we deal with. And typically in Ethernet, we're dealing with 2 major packet sizes at the end of the day. We've got the standard MTU, which is around 1,500 bytes, and we've got jumbograms, which is around 8 to 9K in bytes of size that's out there. So our messages are packed into those and shipped onto the network. Now, if we lose multiple of those, we've got to recover them as multiple packets. But with Aeron, it's data went missing in an offset for a given length, so we just send that back, and that'll end up having the data retransmitted from that point forward. So what if the multiple packets that are lost spans like multiple datagrams like this? We have to retransmit the multiple datagrams to get from the source to the sender to fill in the lost data. So how does this play out? So considering that with unicast, we've now gone to immediate NACs. So not multicast. The multicast world is still the multicast world. But in the unicast world, we used to send immediate NACs all the time. But we started to see some differences with certain types of customers. And part of the nice thing was seeing the success of Aeron is it's used in lots of new and interesting ways. And lots of those new and interesting ways cause new and interesting behaviors in the product. So 144 has a new feature that whenever we detect a gap on a unicast stream, we don't send the NAC immediately. You might think, well, why? That doesn't make sense. We'll get into it in a little bit more detail, and it's particularly important when you start having larger amounts of data loss. And if you don't have large amounts of data loss, it's actually still kind of great when you're NACing immediately. So don't really need to rush to upgrade, although it's kind of nice if you do upgrade and get lots of new features. We don't lose any data, but we get some interesting behaviors with the old way of doing it. All right, let's work through an example and show what this means. So if I've got an immediate NAC, just to make the numbers nice and simple to understand, we're going to assume packets are only 10 bytes in size, because that makes for nice, easy calculations in our head, not the 1404 bytes or whatever we'll be getting in an Aeron MTU by default. So we're sending packets, and you can see in this diagram, like I've sent 2 packets, and a third packet gets sent, and now I've got a gap. That gap at the bottom, which is this gap of 100 bytes, starting at offset 20, going through to offset 120. that means there's 10 packets have gone missing somewhere in the network. Now, maybe it's even more than that, but 10 packets makes it kind of interesting. So the NAC goes out and the sender sends back all 10 packets because it can do that. I've had the NAC, I've had the range. It goes, okay, I fill that range, I send 10 packets. But remember, time is a thing. Latency is not zero. This is where it gets quite interesting. And it gets even more interesting in a system that's very fast, like Aeron, that it reacts to stuff really quickly and really responsively. And that proves interesting in many other ways. Like, grab me for a beer later and I'll talk about the interesting things we find running in the likes of Kubernetes, for example. And you've seen you have strange twitches and stuff for a while. So these packets are all flying across the network and they're arriving and going straight into the log buffer. And the system is observing this thing being rebuilt. Now, it's realized that that packet got in there first. So the position 20 to 30 get filled. But I still have a gap from 30 up to 120. So I've got 90 bytes still missing. Now, remember, we immediately NAC. So shouted, missing data. Sends it back to the source again. Source will have to retransmit more data. And so it does that. Now, it looks in a very simple picture here. So I've now got a retransmission that's going to go from 20 for 100 bytes that's happened before. Now I've got this extra data. So it's coming. So that's been filled in. Next packet goes in again. Can anybody spot the pattern that's going to happen here? Have anybody heard the term accidentally quadratic? Guilty. We went accidentally quadratic in this. But what's really interesting is virtually no one noticed for 10 years. Because this is the problem about being too quick. When you're actually really, really fast, people don't even notice when you screw up. Maybe there's something to be said for that. But what happens is all of these packets end up going with all of these separate NACs. So these are all individual NACs flying back the other way. So what ends up happening is this is the actual amount of data that gets retransmitted. Now, Nate's American, so he's showing the American office here. Guy goes, substitute in Ricky Gervais, same idea. But yeah, all this data is flying across here. So what do we do? Steal another idea from the US, cone of enlightenment. Let's go think hard about this. Well, I didn't actually have to think very hard about this, but it's kind of obvious when it's pointed out. We basically got to solve this. We've got to throw some engineering at it. So what's the right answer? Well, basically steal lots of the good ideas from the multicast stuff that actually do apply in the unicast side. So rather than random backoffs, just pause a little bit. Sometimes it's actually worthwhile just taking a breath. Because Aeron's really fast. And if it's getting all this data, and like all that data is arriving, just as soon as you see that the data is there, or some of it's there, don't just scream straight away. Just like give it a minute to settle. Actually, give it a microsecond to settle, usually. And all of a sudden, the rest of the buffer gets filled in. And then you don't have to react and send the NAC straight away. So we introduced a new thing with the initial delay and the NAC retry delay, because NACs can also get lost. So you've got to resend those as well to be reliable. So one of the config options now we have is, by the way, has anybody ever adjusted the retransmit figures inside Aeron? Probably not. Now, you probably could be getting a bit more latency than you expect in certain environments. Like, we put the original figures in over 10 years ago, and most of that work was based upon research that Todd had done 15 years previous to that. So some of those constants are a wee bit out of date. Like, we're expecting the typical data center to have a sort of wall-to-wall latency across the data center of about 60 milliseconds. It isn't these days. It's a lot less. So the constants have been changed to 144. So we're not being overly optimistic, but we've turned them down to around 10 milliseconds. But you probably want it to be even less than that. So our initial pause is an order of magnitude less than what we'll do in the retry, and the retry is around about 10 millis around that. But you can look at tuning that for your environment. So the likes of Stefan going across his data centers, he's looking up in the milliseconds for doing that because he's crossing data centers, the latency's at. Some of the people who are in colos with cut-through switches and various things, you're down in microseconds, and so you just change the config. So yeah, some of the stuff is worth changing to get the really sorts of good behavior you want out of the system. So with the default config, taking the previous example, if we do the media NAC approach, we send 10 NACs and we have 55 retransmissions. With the new algorithm that's in place, 1 NAC, 10 retransmissions, exactly what you want to have out of this in a simulation. So it gives us exactly what we want in this sort of behavior. And why are we doing this? Well, the world's going to the cloud. And we're getting to see this a lot. So lots of our customers in colo have really cool switches and all that sort of stuff, but also a significant number of our customers are in the cloud, and cloud has higher latency, and particularly when you go across regions and go between cloud environments, you get more loss. So this got pointed out a lot to us in the last year, where people especially are going into these more complex environments. They're seeing that, yeah, we know latency sucks in this environment, but sometimes it seems to be sucking a bit more than we hoped it would. We look into it, we find there was actually loss events happening, and the loss events were over quite large ranges of data, and as we recovered them, it was taking longer than it should have taken to do that, and that's why the fix went in. So we make mistakes too. And I think the point of some events like this, I think it's important to share mistakes, because it's how we all learn. And so to show that some of the stuff's hard and getting it right is kind of interesting. And on that, I'll thank you very much and take any questions.
So I have a question. If you send something on a longer distance, does Aeron kind of detect in some way that you can tweak the delay or do some adjustments, or we still expect user to finely tune, knowing what it's 10 millis between endpoints and not 1 micro. So you still expect user to fine tune it so that achieve better performance, or there is something Aeron does for you to kind of adjust to different distances when you send.
Yes, so good question. We don't do the automatic adjustment to distances. So it's one of the things that TCP does a little bit with its auto tuning, but even its ranges can be not sufficient in some cases. So we generally are expecting people to know roughly what the latency is in their network. Same with multicast, knowing the rough group size. We have defaults in there. So we accept a group size of 10 as our default. You can change that, which is kind of interesting. So if you have multicast and your groups are 3 or 4, you probably want to change some of it. Though it won't behave terribly, you just won't get the optimal out of it. And it's the same with the latencies on that. Your normal throughput won't typically be that much effective unless you're up at the limits of things. So you tend to get fairly good behavior on that. So getting it wrong will cause possibly some loss, some tail problems, and not get you the ultimate throughput. When you turn on congestion control, we can be doing some of that. So part of what we do is measure round trip time with Cubic, and this is one of the things that's coming in with BBR v2. That's why it's influence quick and HTTP3 is to actually do some of those automatic decision things. We have all the hooks to do that. So that could be an interesting piece of work if people have networks that are more unpredictable than they know. And I think that's probably some of the world that we're going into. If many of our customers were in data centers of colo with very predictable latencies, you can set this all up. But to start running many different cloud environments that can be very different, also offering some auto tuning in the future is probably a good way to go.
Thank you very much.